in statistics. Know the famous in this video we're going to integrate e to the negative x squared. But I'm not going to tell you guys to pause the video and try it first because no matter what you do, you cannot find answer to this integral by using elementary functions. What I mean by that is you cannot find answer to this integral by using your regular trig functions or inverse trig functions, hyperbolic trig functions, or exponential functions, logarithm functions, radical functions, power functions, whatsoever, or any of the combination above. It's not possible. In fact, it has been proven that this right here is what we call non-elementary. Sometimes it's good, it's helpful to know some famous ones. This right here is certainly a famous one. It happens a lot in statistics. Know the famous ones so you don't spend the time to integrate this with your usual techniques. It's not going to work. So in this case, we actually have two ways to answer this. The first way is, of course, you can just say this right here has no answer, but in this sense, this right here you can put down non-elementary. Like, for example, in Calc 1, Calc 2, or Calc 3, this is perfectly okay. But if I just say, hey, this has no elementary antiderivative, then you guys will be mad at me. I don't want that to happen. So the second way to deal with this is that we can invent some new functions so we can continue our study. And the new function that we're going to use is what we call the error function, and the abbreviation is ERF of x. But not quite. There is actually some constant multiple in front. And what's a constant multiple? It's right here, square root of pi over 2. And you might be wondering, why is this the case? And now let's talk about this in detail. First of all, this is called the error function. And once again, I will just call this to be the ERF of x. The official definition is that ERF of x is defined to be, yes, you have to talk about the integral. So I will have the integral from 0 to x, right? Because the input here is x, I want this to be x as well. This right here is my variable. But if I use x right here, I cannot use x right here, like, to be technical. So just change the variable, let's say t, e to the negative t squared, and then we just put down dt right here. But hopefully you guys have seen my previous video. If you guys look at this curve right here, and let me just draw that for you guys real quick. E to the negative t squared. In my previous video, I used x, but in terms of the curve, doesn't really matter. The shape is the same. Looks like this, okay? So this is the graph of y equals to e to the negative t squared. And one of the property of this is that the whole area under the curve right here, the whole area is surprisingly square root of pi. It's square root of pi. It's really cool. Once again, if you want to see how to do that, you can check out Dr. Payan's video for this. You have to use calculus 3 to show this. All right. When you have the integral from 0 to x, means that you begin at 0, and then suppose x is positive, then you go to the right direction. So you can just say it's right here. And what this is doing is that you are keeping track of the area from this part to this part. And this is the blue version, the blue portion right here. All right? So this function is pretty much keeping track of the area. But in statistics, what we want is
the whole area under the curve to be 1.
Why? Because what we call the probability density function. Just a quick example is that the whole probability is 100%, right? That's pretty much the idea. So we want to have 1. So instead of the whole area being square root of pi, but technically, since I started at 0 to x, if you have x goes to past the infinity, this right portion right here is just square root of pi over 2. But as I said, I want to have 1. So I can just multiply by 2 over square root of pi, like this. And as you can see, the error function is defined to be this. If you want to integrate this guy, you can just multiply by the reciprocal, namely you get square root pi over 2 ERF of x for the answer of that. All right? Okay, and once again, this right here is pretty much a reciprocal of the right-hand side area. All right? So This is not good enough, I know. I will do more for you guys. Perhaps the best way is I will show you guys the graph of this function, because graph is one of the best ways to visualize how the function behaves. It gives me so much information, right? But with that being said, we have to do more work as well. So it's okay, let's do it. First of all, x right here can be positive or negative. If you went to the negative side, when you go from 0 to negative whatsoever, you can just flip the integral if you like, so it doesn't really matter that much. But the main point is that x can be anything for ER f of x. Therefore, if you want to talk about the graph of ER f of x, first of all, let's talk about the domain, which it will be from negative infinity to positive infinity. Okay, so that's good. We can plug in any x values that we want. And secondly, let's find out the horizontal asymptotes, shall we? Therefore, let's go ahead and take the limit as x goes to negative infinity first. And for this function, let me just put this down. Namely, we have 2 over square root of pi times the integral from 0 to x. And then we have e to the negative t squared dt. And you see, when you have this right here, you technically can plug in negative infinity to here. This is where the x is. So this is going to look like 2 over square root of pi, integral from 0 to negative infinity, and then this is e to the negative t squared dt. And this right here is what I was saying, it's kind of out of order, because right here, you should have a smaller number down below, but you have negative infinity right here. That's no good, but it's okay, it's an easy fix. What we are going to do is, I'm going to multiply by negative, and then flip this order. That's pretty much it. So I will still keep this. This is 2 over square root of pi, and I flip the order. It becomes the integral from negative infinity to 0 of this, of course, e to the negative t squared dt. What's this right here? If you look at this picture, when you go from negative infinity to 0, this right here is still square root pi over 2. So this right here is still square root of pi over 2 multiplied by 2 over square root pi, you get negative 1. So you have the first horizontal asymptote at y equals to negative 1. And if you take the limit as x goes to positive infinity of this 2 over square root of pi, and in fact, you know this right here is actually an odd function, so the answer is going to be positive 1. But it's okay, I'll show you guys this right here anyway. This right here is going from 0 to x, e to the negative t squared dt. And of course, you plug in infinity here, you get 2 over square root of pi, and you have the integral from 0 to infinity here, and then you have e to the negative t squared dt. And this right here is just square root of pi over 2, which is going to give you 1. In fact, you have 2 horizontal asymptotes. So let me just write down horizontal asymptote based on our computations. You have y is equal to negative 1, and the other one is y is equal to 1. So you have these boundaries, okay? And now, let's see if there's any vertical asymptotes. But since the domain was all real numbers, so there's none. And let's talk about first derivative. This is the fun part. Let's see. I will look at the function. I will just write down ERF prime of x. How do we differentiate this function? This is just a constant multiple, so you just leave it 2 over square root of pi. And by the fundamental of theorem of calculus, part 1, right? So I will tell you FTC part 1, okay? All you have to do is put the x right here. That's it. And the derivative integrals pretty much cancel each other, and you put the x right here. So you get e to the negative x squared, like this. That's it. Seriously, it's just that easy. This is my favorite, the calculus 1 question. And if you look at this, and perhaps you can do what we did last time, if you set this to be 0, well, you don't have any critical numbers. So I'll just tell you, no critical numbers. And in fact, this right here, it's never 0. And you can actually say more. This right here is actually always greater than 0. And with this, we can say that this function is always increasing. So let me just write this down. The error function is actually always increasing. And now let's move on to the second derivative. So I will look at this and differentiate, and I'll write down ERF prime prime of x like this. Well, all I have to do is look at this and differentiate, but this is the constant multiple. I can write it down first, 2 over square root of pi, and then derivative e to the something is always that, so e to the negative x squared, but you have to use the chain rule.
Use the chain rule!
So I have to multiply by the derivative of that, which is negative 2x like this, and right here, I will set this to be 0 so I can find out the potential point of inflection. And if you look at this, the only way that this can be 0 is when x is equal to 0. So I will tell you, we care about when x is equal to 0. And then from here, we can go ahead and do our second derivative test like this. So I mark it as 0, and now let's pick a number less than 0, let's say negative 17. Plug into here, negative 2 times negative 17 is positive, times the rest is positive, so right here is positive. And then pick a number bigger than 0, let's say 25. Plug into here, negative 2 times 25 is negative, times the rest positive, so altogether still negative. This right here is negative. So what does that mean? This right here tell me concave up, okay, CU stands for concave up, from negative infinity to 0. And then concave down, so I put on CD like this, from 0 to positive infinity. And then we do have a point of inflection, so I put on POI like this at x equal to 0. So now, in fact, with all this, I can show you guys the graph. And I will do the graph right here, and I'll show you guys the graph on the screen. So I'll just put this down right here. I know it's a small one, but it's okay. First of all, domain is all real numbers, and let's see. Everything is increasing, and perhaps you can find out some, like, seriously, just have some numbers, yes, so you can know where to graph this. Put 0 into here, you get ERF of 0. You put 0 here, 0 to 0, you get 0, right? So you have 0 right here, okay? And let's see, we have the horizontal asymptote, so let's indicate this. We have negative 1, and then we have positive 1, like that, okay? So this is positive 1, negative 1. And let's see, the function is always increasing and concave up from negative infinity to 0. So from here, it's concave up. So let me just do like this, concave up. And of course, horizontal asymptote, you don't touch that. It's concave up like this. And then it changes concavity. It's like that. In fact, this right here, it's really similar to the arctangent graph, but I think this is way cooler. This right here is a graph for ERF of x. And you might be wondering, can we find the area under ERF of x? Sure, why not? And why don't you guys try? Maybe you can try to find the area from like 1 to 7 whatsoever, but I will leave that to you guys. But at the moment, this right here is it. And yeah, really cool, huh?
El entumecimiento en tu pie puede estar relacionado a falta de vitamina B. Olvida esta molestia con Neurobión.
Hola y bienvenidos a otro video de Mate Fácil. En este video vamos a demostrar que la integral que va de menos infinito a infinito de e a la menos x cuadrada de x es igual a la raíz cuadrada de pi. A esta integral se le conoce como integral gaussiana y existen varias maneras de demostrar este resultado. En este video vamos a hacer uso de cálculo de varias variables. Vamos a calcular una integral doble para llegar a este resultado. En primer lugar, fíjense que no podríamos calcular esta integral considerando únicamente una variable. O sea, si nosotros tratamos de integrar directamente e a la menos x cuadrada, no podemos, porque para utilizar la fórmula de la integral de e a la b, necesitamos aquí adelante construir la derivada de b. Pero fíjense que en este caso la derivada del exponente es menos 2x. Y aquí no tenemos ninguna x que nos ayude a completar la derivada. Entonces no podemos integrar esto directamente, ni podemos hacerlo aquí con un simple cambio de variable. Necesariamente tendremos que utilizar algún otro método más avanzado. En este caso vamos a hacer una integral doble. Pero antes de empezar con esto, quiero empezar con algunos detalles que vamos a ir usando durante la demostración y que quiero que queden bien claro antes de empezar con la demostración. En primer lugar, Fíjense que esta es una función par. Función par, recordemos que es una función tal que si nosotros cambiamos la x por menos x, obtenemos la misma función original. O sea que si aquí en esta expresión, esta x la cambiamos por menos x, al elevar menos x al cuadrado nos sigue quedando x al cuadrado. Nos queda exactamente la misma función que teníamos originalmente. Una función par siempre va a tener una gráfica que es simétrica respecto del eje y. Aquí tenemos la gráfica de la función e a la menos x cuadrada. Fíjense cómo la gráfica es simétrica respecto del eje y, que es esta línea de aquí. Entonces, nosotros lo que queremos calcular es, geométricamente, el área que hay debajo de esta gráfica, desde menos infinito hasta infinito. Toda esta área de aquí. Queremos demostrar que esa área es igual a raíz cuadrada de pi. Fíjense que como la gráfica es simétrica respecto del eje y, podríamos nosotros únicamente calcular la mitad del área y el resultado multiplicarlo por 2. Así que lo que vamos a hacer es, en lugar de considerar esta integral, para simplificar las cosas vamos a considerar la integral que va desde 0 hasta infinito, o sea la mitad que va de aquí de 0 a infinito, y esa mitad la vamos a multiplicar por 2 para obtener el área completa que queremos. Bueno, ese es el primer detalle. Otro detalle que hay que tomar en cuenta es que en esta expresión de aquí, la x no juega ningún papel relevante. O sea, podremos tener aquí x como variable, pero podríamos tener cualquier otra variable. Podríamos en lugar de x poner y seguiría obteniéndose el mismo resultado. E a la menos y cuadrada por dy es raíz cuadrada de pi, esta integral. O podemos cambiar por la variable t, por ejemplo. La integral de menos infinito a infinito de e a la menos t cuadrada de t es igual a la raíz cuadrada de pi. Es decir, la variable que tengamos aquí en la integración realmente no es importante. Claro, lo único que sí importa es que la misma variable que aparece en el exponente es la que aparece en el diferencial. Y es todo. Entonces, estas tres integrales en realidad son la misma integral. Simplemente le estamos poniendo diferente nombre a la variable. Y finalmente, otro detalle que hay que tomar en cuenta antes de empezar con la demostración es un teorema que se llama teorema de Fubini, que entre varias cosas que nos dice, una de ellas muy importante es la siguiente. Nos dice que si nosotros tenemos una integral doble, donde los límites de integración son de a a b para el caso de x y de c a d para el caso de y. Aquí, bueno, hay que recordar cómo se leen las integrales dobles. La última integral siempre es la que tiene los límites de integración del primer diferencial. O sea, CD son los límites de la variable y, AB son los límites de la variable x. Bueno, lo que el teorema de Fubini dice es que si esta función de dos variables la podemos factorizar como g de x por h de y,